It's my pleasure to introduce our second keynote speaker, Shankar Krishnamurthy. He is the General Manager of the Silicon Realization Group at Synopsys. Shankar is the General Manager of the Silicon Realization Group, leading design verification software platforms of Synopsys. His team innovates across a broad spectrum of EDA technologies, including simulation, static analysis, debug synthesis, sign-off analysis, place and route, test automation, formal verification solutions. Wow, at IRPS, we've really expanded our reach. Prior to his role, he was as general manager of the Silicon Design Group with responsibility for Synopsys, a digital design platform. In earlier roles, he served as senior vice president of the Digital Design Implementation Group, delivering several game-changing innovations, including Fusion Compiler, RTL Architect, 3DIC, TestMax, and TestMax solutions. Before joining Synopsys in 2017, he was at Mentor Graphics, where he served as general manager of the IC Design Solutions division. He joined Mentor in 2007 with the acquisition of Sierra Design Automation, where he was founder and CTO. Prior to Sierra Design, Shankar led Synopsys' physical synthesis and logical synthesis R&D organizations. Shankar received his MS in computer science from the University of Texas, Austin, so he's a local boy, and his bachelor's degree in computer science from the Indian Institute of Technology, Bombay. Welcome, Shankar.
Thank you, Charlie. And thank you all for inviting me to present at the IRPS 2022. I'm really excited to see the audience here in person as well as everybody online. And today my talk is going to be about semiconductor predictability. And why is this important today? I mean, we can see the rapid evolution towards a smart everything digital economy. And semiconductors are the foundation of this evolution. And so the important work that all of you are doing in terms of reliability and resilience of devices and components is really fundamental to enable us to make this transition to this smart everything digital economy. So let me first start with just talking about the landscape around us. And what we are seeing is a rapid digitization of many, many market verticals. Pretty much existing as well as new verticals are emerging where digitization is front and center the focus. Sensors, monitors at the edge are gathering data. That data is being processed at the edge. It's being transported to data centers through wireless and wired networks. And then AI, ML technologies and big data techniques are being applied on that data to generate insights. And those insights are being pushed back to the edge to improve user experiences, to improve results. And this story is repeating itself in vertical after vertical. And we even have some new exciting verticals that are emerging with the recent discussion around the metaverse, which promises to completely change the interaction between humans and computers. All this is great news for the semiconductor industry. If you haven't been paying attention, valuations are through the roof. We are about to cross $500 billion in semiconductor revenue and are well on track to exceed $1 trillion of semiconductor revenue by the end of this decade. This is just phenomenal for our industry. And so all this activity that's happening in these different target markets is translating to more and more design starts. And if we look at what these designs are trying to optimize for to meet these requirements, it comes down to a few fundamental trends that we are seeing. The first one is what we call as PPACT, or power, performance, area, cost, and time to results. And this is across different markets with all the competition that's present, with many different companies competing for very critical sockets. Every ounce of power must be squeezed. The die sizes have to be minimized as much as possible to reduce costs. The market windows are extremely short, and this story repeats itself in market vertical after market vertical. We also see the rise of custom silicon. The whole notion of building custom bespoke silicon for specific workload acceleration is really picking up steam. And we see in several critical markets design of domain-specific accelerators to solve specific design problems and achieve 100x, 1000x type of improvements in power as well as performance. Then we see the trend of vertical integration. We are seeing companies like Apple, Tesla, AWS, essentially building the software stack, the hardware stack, and optimizing the intersection of the software and hardware stacks to extract more performance, more predictability, more power. And this is a trend that is rapidly spreading across many different industries. And then finally, for each specific vertical, there are some key care-abouts that are being optimized for those designs. The data center verticals are really about trying to optimize Fmax as much as possible. In the mobile verticals, area and power are big care-abouts. In other verticals like automotive, functional safety is a big care-about. But something that's pretty much constant is this notion of high availability. And that's where reliability and its cousin, resilience, comes about. Because essentially, these two are really fundamental to make things highly available and always on all the time. So these are some of the key trends that are driving from a market dynamics perspective, and that's driving the next generation of designs. Let's now take a look at it from the supply side. Let's see what's happening in terms of the whole evolution of semiconductors. You have the great Moore's Law progression over the past 3 decades, which has delivered that consistent 2x in terms of scaling, in terms of performance, power gains. And this is truly phenomenal that that trajectory has continued for as long as it has. But one thing that we see recently is that while the gains in density are alive and well, the gains in power and performance are starting to peter off. We are seeing about 15 to 30% is the kind of range of improvements in power and performance in the more recent node transitions, while the density still continues to be very strong. So the question is, you've got all this demand that we talked about in the previous slide for more power gains and more performance, and you have just at the same time, you see this flattening of the Moore's Law curve in terms of power and performance. So how do you close that gap? And that is what we at Synopsys essentially call the SysMoore revolution, which is how do you apply a booster pack to that Moore's Law curve in order to bring that curve back up with respect to delivering the gains in terms of performance and power. And that really comes from 3 different concepts. First and foremost, domain-specific accelerators. I mean, you all have been following the evolution of the TPU, for example, from Google that has significantly accelerated machine learning and AI workloads. And there are similar domain-specific accelerators being built for just augmented reality, virtual reality, and applications like that. Then there is the advent of 3D IC, which is the ability to put multiple dies on the same package, and whether it is stacking them or putting them side by side, and thereby dramatically improving latency, gives us a way to significantly improve the performance of systems. And third is the application of AI to design flows and to architecture development, which again promises a big gain in terms of performance and power. So this is basically what we call SysMoore, but there's another challenge we have to overcome, which is the challenge of engineering resources. So while we have many, many new entrants in semiconductors, many more designs being done, the total cost of designing a chip from 7 nanometer to 5 to 4 to 3 is just skyrocketing up. The total number of engineers in the world is not sufficient to meet all the silicon ambitions of all the semiconductor companies. And so everybody is looking for dramatic improvements in workforce productivity, new applications of AI and machine learning to automate design, and thereby significantly accelerate workflows, which then enables these ambitions to be met. So these are the twin challenges that design teams are dealing with respect to meeting the ambitions we spoke about in the previous slide. So at Synopsys, we have kind of mapped all these challenges into a roadmap, which really has 6 vectors. And the reason you see that cross in the middle is really the multiplicative force of progress across these different directions will give us the kind of gains that the industry is expecting from Synopsys, who's a design enablement and design automation supplier. So first is, of course, how do we enable the development of these domain-specific accelerators? And it's really about providing exploration environments where architects can rapidly look at different architectures and microarchitectures to make determinations of the best power and performance that's available for accelerating specific workloads. Second is, of course, the focus on power. Across every vertical market, the importance of power cannot be underestimated. And so the whole problem statement of optimizing for power and energy as an end-to-end problem, all the way from software down to devices, is becoming a front and center focus for many, many companies. And there's a lot of great work that's happening across that spectrum to deliver significant gains in power. Third, the Moore's Law is alive and well, and let's keep supporting it. Our foundry partners are doing an amazing job of continuing to deliver on that density scaling. And so there are several new innovations that also Mohsen spoke about in his previous keynote, and all those have to be supported and enabled for the industry to benefit from. Then the transition to 3D IC. As the industry transitions to 3D IC, a new design environment is needed for the development of 3D ICs. How do you enable an architect of a chip to rapidly explore different configurations in terms of looking at different dies, at different nodes, potentially stacking them or keeping them side by side? How do you get feedback on system level performance and energy consumption? So the ability to rapidly explore 3D IC architectures, to construct them, and then to analyze them, you need a new design environment to enable this. Then comes something that's very relevant to this audience, the silicon lifecycle. Essentially, the whole notion of measuring reliability and resilience of systems and then optimizing them from end to end, all the way from a device component layer, all the way to system level in-field functioning, is becoming very, very central. And so the approach really has to be holistic. I was really glad to hear in Mohsen's talk as well, talking about the fact that this is a full stack problem. This is not something that can just be solved at the device level or at the circuit level. It really needs to be solved as a full stack problem with every layer of the stack contributing towards building more reliant systems. And then last but not least, with the advent of AI and cloud, we have an opportunity to significantly accelerate workflows. Cloud offers the ability to scale, which allows us to scale many, many problems in our domains by several tens of X. And then AI offers the ability to do things autonomously. And so by being able to do autonomous design, we dramatically improve the productivity of engineers. So this is basically our roadmap that we are executing against. And the multiplicative effect of the progress on all these different directions helps us to solve some of the challenges that we looked at earlier. Now, specifically, and you will see that again, the talks of both Mohsen and myself are very aligned in terms of some of these problem statements, because we hear the same thing from our customers as well, is the importance of robustness for data center applications. And there are several papers that were published in the last few years, both from Facebook as well as Google, talking about essentially silent data corruption. And the problem statement here is when you have deployed millions, tens of millions of servers, even having a 1% error is catastrophic. And the reason it's catastrophic is on top of these data centers is this expectation of high availability. And any form of catastrophic failure takes down large systems. Just imagine Instagram or imagine Facebook being taken down, and there will be a riot on the streets almost. That's the kind of dependence we have on these high availability type of environments. So I think this whole notion of being able to manage the reliability of these systems at scale is becoming very, very important. And so the ability to rapidly root cause, and then the resilience factor, which is to really to have feedback that a system is performing below expectations so that some mitigation steps and measures can be taken, is also very critical in order to address this challenge. There is a similar problem as well on the automotive side. And the modern automotive is quite the marvel. More than 1,000 microchips embedded, large subsystems which are communicating with each other over high bandwidth networks. You have your connectivity domains, communicating with your ADAS domain, connecting with your in-vehicle infotainment domain. And the sensors which are on the automotive are generating gigabytes of data that are being processed by machine learning systems on the automotive itself in order to basically create insights and make decisions about where the car should move or what pace it should go at, and so on. And so what you have here is a very complex system of systems. And again, the reliability expectations are significant. And the whole conversation in this industry has transitioned from defective parts per million to defective parts per billion. And the same holds true even for the data center market. And here, obviously the cost of an error is obviously could be very unfortunate. And so the whole notion of really reducing errors, improving reliability and resilience really rings home for these two very, very important markets. And that's driving a lot of full stack innovation in these areas. So let me now start by just kind of building bottom up. What are the different points of failure affecting the product lifecycle? So of course, there are failures at the device level, and you all are the experts at that. There are failures at the die level, as well as failures at the package level. And then there are different types of failures that can occur across these three classes. Manufacturing failures, electrical failures, environmental failures, as well as mechanical failures. So if we look at just to define these different failure mechanisms, the manufacturing or process-related failures are largely due to variation, and silicon variation is really becoming a major, major issue at advanced nodes, and the ability to accurately predict the performance of the final manufactured silicon in field is a huge first-order problem as companies are looking to do chips at the latest nodes. We also have other types of issues, like contaminants in terms of the process itself, which can cause different types of errors as well. Then you have electrical failures. Electrical failures due to aging, HCI and BTI, electrical failures due to ESD, failures due to electromigration, and these all have to be mitigated in the process. Third, mechanical failures, and this happens due to issues like stress, warpage, fracture, and just the ability to essentially be able to deal with all the mechanical challenges that come about in building these complex systems. And then finally, you have environmental failures. And this obviously can be both terrestrial as well as extraterrestrial, and the presence of different types of particles that impact the functioning of the circuit, causing either soft or hard errors. And again, this is a big cause of errors. And one of the data center papers that we looked at earlier did point to this as a possible cause of the silent data corruption problem as well. So these are the different types of failure mechanisms. And I can speak from a EDA perspective, electronic design automation perspective, that our approach to dealing with failures in general has been through the whole test and test automation side of the world. So basically, if you look at what has been done with respect to design flows to really outfit them for reliability and for resilience, we've really had three different workflows: test at the silicon level, test at the system level, when you essentially kind of bring up your after you've done all the burn-in tests on the tester, and you're now bringing it into the system, and you're booting up your OS, you're running your applications, and then test at the in-field level itself. And these are the different types of classes of errors that are detected for each of these classes. You can see that many of these are caught by different stages. And so essentially, by having your tester run your ATPG patterns, your functional patterns, and by sweeping your frequency voltage ranges, you essentially try to detect what are all the different types of fails. And then we use a variety of techniques to essentially deal with that. One is, of course, parts binning, throw away the ones that don't work. The second is we basically build embedded repair mechanisms. So we talked about ECC in memories. There is similarly repair mechanisms for logic. that is basically built in to kind of offer a source of redundancy and to self-repair. And then the third one is really margins. I mean, when you don't understand something fully well, you can't predict something fully well, you just apply margins in the process. That third one is under a lot of pressure these days because the competition is so intense between different companies, different players. Everybody is on a warpath to strip margins out of their flows and really try to push the power, the performance. And so if margins get stripped out and you still want to build reliable components, then you really need much more improved modeling that needs to move upstream into the design process. Otherwise, you will compromise on reliability. So really, what I'd like to do now is we have a great toolbox that we've built over decades in the reliability and the resilience space. And I'd like to propose a few additional tools to add to that toolbox in order to meet some of these ambitious goals of defective parts per billion. And so those new tools, they may not be new to you, but just to kind of put it in perspective, really fall into 4 different buckets. One is this whole notion of design robustness, how to left shift the whole process of robustness into the design world so that when designers design chips, they're aware of it and they center their designs in some way to make things better downstream. Second is fault simulation and the introduction of fault simulation to workflows. Third is in-field analysis and optimization. So how do you get feedback from the chip when it's running in field and basically take some actions based on that? And then the last one is really how do you treat a collection of designs, a collection of chips working together in a large installation like a data center as a fleet? And then how do you manage that fleet from a predictive maintenance perspective? So these are the 4 additional tools that we would like to propose being added to the toolbox. So just going into each of these in a little bit more detail, the whole notion of robustness analysis is if you're doing an advanced node design today, I mean, variation is something that you have to embrace. And so how do you make a design that in spite of all the variation that's going to come downstream with respect to the process technology or voltage variations or other types of things is still going to function the way you expected it to function? So that's one area, and you have to left shift this problem into design versus trying to deal with it just at a device level. Second is fault simulation, right? So traditionally, these disciplines of test and ATPG and functional simulation have been quite separate. But in reality, to truly test your device when it comes back from the fab, you put it on a tester, you run your ATPG patterns, you run your functional simulation patterns in order to get a confidence that things are okay. Well, if you could now co-optimize these domains, you could probably do better. So that's the second big idea that we would like to propose. Third is the in-field analysis. So essentially, when your silicon is running in field, like in a data center or in an automotive, how do you get feedback on how it's performing? When different workloads are being presented to it, how is the underlying silicon performing? And so this whole notion of introducing sensors and monitors into the chip so that we can get real-time feedback on how the silicon is performing on different workloads and how it's performing over time, and then taking mitigative action based on that is a new concept that we would like to introduce. And then last but not least, how do you use the power of AI to really bring this whole notion of predictive analytics and predictive maintenance to this whole problem statement? So let me start with variability analysis. So today, when someone is trying to build a chip for an automotive application, let's say, with high reliability, the traditional approach is you basically kind of design with either 3 sigma or 5 sigma libraries, and then you kind of do the design with confidence that as long as I meet my 5 sigma requirements, then the resulting chip should be okay. But the kind of the downsides of that approach is it brings a lot of pessimism into the design flows, and so you sacrifice your PPA in a significant way. And the correlation which finally shows up between the functioning of the chip and its performance on silicon is still not great, even with these approaches. So it's a big hammer. It's what the industry does today, but there are several downsides to it. So essentially, the proposal that we have is to really left shift this robustness problem into the design space by introducing methods into the design flows, like, for example, taking your critical paths and subjecting them to high sigma Monte Carlo simulation and ensuring that essentially these critical paths are still going to function just fine even in the presence of high sigma type of behavior. And how do you kind of really make your design more robust to do that? By fixing the right bottlenecks that show up from that high sigma Monte Carlo on the critical paths, and essentially kind of outfit the design with those robustness methods. Similarly, for voltage variation, again, by using voltage scaling and voltage scale libraries, you can rapidly sweep your design performance over different voltage fluctuations, and then make the necessary changes to the design to essentially withstand a larger voltage range than what it was implemented at. So essentially, the problem statement is, let's take many of these things that are going to cause variation downstream. Let's left shift it into the design space with models, and then let's optimize the design with those models so that we can bring down the margins, not sacrifice PPA, and really make sure that the design can withstand variation in voltage, variation in VT, variation in ID-SAT, variation in metal migration, and so on. And thereby, you just deliver a more robust design downstream. Similarly, with aging analysis, if you look at the current methods for aging, essentially to model your hot carrier injection or NBTI, the traditional methods have been either ignore it or just margin the heck out of it. This have been the typical approaches to deal with this. But again, with growing sophistication, we are now able to really provide a much more sophisticated solution, where rather than the older approaches of just having libraries characterized at the 5-year, 10-year, 15-year, 20-year mark, and then trying to close your designs with all those different libraries, we now have much more sophisticated approach where, thanks to machine learning and all the recent advances in statistical modeling, we can actually create aging libraries which fully capture the emission profiles, the stress waveforms, and then use those aging characterized libraries in your static timing analysis frameworks to then measure the performance of the underlying device under different conditions. And the correlation that we see with this approach, where we use ML models to essentially get the aging approximated delay, is very, very good compared to an approach which fully characterizes the library for each of the different aging scenarios. So these types of methods are now entering mainstream design flows. And again, under the overall umbrella of how do we left shift this problem into design, and how do we build more robust designs, these are like some powerful new steps that are being taken to both move away from the margin-based approach and to bring more sophisticated models for reliability upstream into the flow. Then we look at the whole problem of just how do we kind of bridge between ATPG and functional simulation. And in a pretty iconic paper way back in 1992, it was clearly established that just your failed scan and IDDQ tests are not adequate. You also need to be looking at your functional test results on the tester in order to determine all the different sources and causes of manufacturing fails. And so what fault simulation brings essentially is it connects these domains up by essentially driving all the different test faults lists that ATPG generates into your functional simulation flows. And then basically you augment your functional simulation test benches to achieve as much coverage as possible of your faults. And then you can really compress the total pattern set that's going onto your tester between the functional and ATPG patterns, and thereby reduce the time and the cost of test. So this is something that across the industry we are seeing is being mandated for the design of of extremely high reliability parts in automotive and other sectors. And this is mainstream now in many, many flows, the usage of fault simulation. So far we've been talking about design and manufacturing and volume ramp and errors related to that. But an equally important step is really, okay, now the chip is in the system, it's out there, it's functioning, and bad things can still happen. And so how are you going to essentially ensure that when bad things do happen, there is a feedback mechanism so that we can really make that bathtub as broad as possible, right? Really prolong that mean time to failure and have a much more graceful degradation versus having some sort of a catastrophic failure. So the concept here is really that we can no longer be blind to what's actually happening within the chips. And so the approach is really on how to augment the design with additional sensors, monitors, in order to essentially get feedback on how the silicon is functioning across different workloads, as well as over time, and then have mitigative action being taken when some not so good behaviors are being detected. So that's the basic concept. So now how do you operationalize this, right? So essentially, the main concept is we are going to be now augmenting the design with monitors and sensors. And the first example of how to do that is essentially in terms of the in-field optimization of performance. So the first type of monitor we'll talk about is what we call as a path margin monitor. And so the idea here is that on a typical design, there are maybe something in the order of a few thousand paths of consequence, right? Speed paths, whole critical paths. And you really want to watch these paths very carefully in terms of how they are performing for different workloads and also how they perform over time so that you can basically take corrective action and you know that something bad is happening. So the basic concept here is we infuse the design based on static timing analysis with what we call as path margin monitors, which essentially apply monitoring capability to specific paths in the design. And then while the design is functioning, you basically get feedback on how those paths are doing with respect to the original constraints, right? So maybe initially you can see that those paths are just fine, and the paths, the setup requirements are being met. But over time, maybe there is some aging that's going on, and the transistors are slowing, and therefore the arrival time starts to degrade, and you get some signal that hey, these paths are now slowing down and are going to impact the performance. So essentially having this type of monitor, and again, it has to be non-intrusive, because if you have to give up PPA in order to get this type of monitoring, then most design teams will basically push back against it. So by having a non-intrusive operation and by having this continuous monitoring, we basically get these additional advantages of not just being able to do some sort of a proactive mitigation measure, but also to be able to potentially optimize the power or optimize the performance. If you find that the paths are comfortably meeting their requirements, then there could be a signal that's triggered to lower the voltage and thereby reduce the overall energy consumption of this chip for this specific workload. So this type of kind of agile type of an approach where you're adapting to the workloads and changing the behavior for workloads is really the next frontier with respect to reliability from our perspective. Now, similarly for power, you could do something even more sophisticated. So you can now augment the chip with a whole bunch of monitors, your process monitors, your voltage monitors, temperature monitors, and path monitors. And then all these monitors can be embedded in different subsystems. The signals from these subsystems can be aggregated in a sensor hub, and then that can then be read out and analyzed both for actions within the chip. Like, for example, if you want to do DVFS, dynamic voltage frequency scaling type of operations, you could take some actions based on that, like lowering the voltage. Or if you see the temperature sensors reporting that the temperature gradients are shooting up, you can take some mitigative actions right there, like you're throttling your frequency. And then you could also signal off-chip with respect to indicating that a particular workload is really causing a certain type of behavior, so that you can essentially get feedback on what types of workloads are stressing this particular device. So just having that closed feedback loop between the actual workloads in the field, back to design, back to the software stack, are all part of this full stack approach towards reliability versus just treating it as sort of fixed and one and done type of an approach. So now if you aggregate this over tens of millions of servers or tens of millions of automotive, then essentially what you get is this whole notion of a fleet management problem. So if you can now get these signals from every one of these devices delivered off chip, and those are now aggregated in a big data cloud framework, then you can mine this data for anomalies. You can mine this data for predictive maintenance type of feedback. And then essentially this is how companies like Tesla and Apple and AWS and others have implemented large systems at scale to really manage and monitor reliability at scale. So this whole notion of that bathtub curve and essentially prolonging it with preventive measures, adjusting workloads, or adjusting, or recommending maintenance whenever something is not functioning as expected, or being able to localize a particular lot of chips that are not behaving the way they should be to give feedback to the vendor. All the stuff is now enabled by really bringing this big data AI type of an approach to the signals that are coming back from the different devices. So this is really what I meant by a full stack approach to reliability. Is you work on it at every layer of that stack, working from transistor up, in fact, materials up, all the way into the software layers to prevent and maximize the mean time between failures. So just to summarize, the essence of what we're talking about today is that we want to add new tools to the toolbox to really make this a full stack problem. And then we have to really have an end-to-end perspective, right? We really have to think about this from materials to software stack, and we have to connect all these pieces together. We can't just solve these problems independently and have that data just be lost from stage to stage. And so the whole notion of having a data platform that can aggregate the data from in-field operation, from volume ramp, from design, and then be able to cross-correlate across these different domains in order to rapidly root cause is an integral part of a full stack approach towards reliability. Let me now talk a little bit about just the Synopsys investments in this area, right? So Synopsys is relatively a new entrant in this space of reliability and resilience with our Silicon Lifecycle Management solutions, but we have rapidly kind of expanded our portfolio of offerings. Everything from design, where we are very, very strong with the Fusion Design Platform, and where we are now inserting these monitors and sensors into the design in a PPA neutral fashion. We are optimizing for design robustness, we're optimizing for aging, we're optimizing for variability as part of the design process so that we left shift the problem that I spoke about earlier. The whole notion of fault simulation, where we bring the ATPG and verification disciplines much closer. We have several products that do that. Embedded in-chip monitoring, we have specific IPs that we have created to monitor process, voltage, temperature, path monitoring. These are IPs that customers are integrating into their designs. We have capabilities that allow you to do volume diagnostics and debug, both in terms of new product volume ramp, as well as large-scale manufacturing and product engineering feedback with respect to where the failures are and rapidly root causing the cause of the failures. Once you have that monitor and sensor data, you need to be able to take it off chip to do all the analytics and fleet management that we spoke about. So high-speed IP to extract that data off chip in order to aggregate and do that big data analytics. And then last but not least, the whole notion of really being able to bring AI into these as a software agent into the software stack, and then be able to adaptively adjust the voltage, adjust the frequency based on the workloads. These are all integral elements of our offering for a full stack reliability solution. So in conclusion, let me wrap up with my closing thoughts here. Firstly, I think the whole notion of, as I mentioned earlier, reliability and failure mitigation, this is really central to the emerging digital economy. It really lays the foundation, and it's so important, the work that all of you are doing in order to enable this, because this is really laying the foundation for a new digital economy. Second, we talked about the silicon failure span, really the whole spectrum, all the way from materials through transistors, through gates, all the way to design, to in-field operations. And so having a a broad end-to-end view is absolutely essential. Third, the approaches that we talked about essentially augment our failure mitigation toolbox. We have a few powerful methods today, and we talked about a few additional methods that could be added to our toolbox. And then last but not least, I think the whole notion of connectivity and traceability across the life cycle is absolutely essential in order to have a holistic approach towards this problem.